Hello class, this is a video tutorial on differential equations part 3. In this video we'll be looking at derivatives that are a function of itself. So some derivatives can be expressed in terms of the original functions. By this, here's a simple example. Y equals e to the power of 4x. Notice that its first derivative, 4e to the power of 4x, it contains the original function itself. So its first derivative can be expressed in terms of the original function for y in this example. So although this is an obvious example, differential equations presents problems with more complexity. We solve these as previously seen, but it may require further steps to make y the subject. Okay, so here are the 3 examples which we will be covering. You can pause this and give this a go at any time you like. So let's get straight to it. So for this, always remember that we can always express the first derivative as dy on dx. And from here, I'm going to multiply both sides by 2y. So I get 2y dy. And at the same time, I'm left with 1 dx, which at this point I can let you know that you may see it as just dx. Integrating both sides, we get y squared equals x. Now at this point you can put plus c here as seen previously, or you can wait until the end where we take the square root like this and put plus c on the outside, or even place it inside like this, because depending on where we place it and if the question provides us with some initial conditions, the value of c will be equivalent depending on where you place it. So either it's in the inside of the square root or the outside of the square root. They're both correct in that you will get equivalent values for c depending on where they're placed. For me personally, I prefer placing it outside like this. All right, so there's the solution to our differential equation here. Okay, so let's move on to the next example. Okay, so this one's already expressed as dy and dx. Let's actually solve this a little bit further. I'm going to divide by y. So I get 1 on y dy. And on the right hand side, I get 8 dx. Integrating both sides, I get ln of y on the left hand side and 8x. Now, here's the exception of where we place the plus c. If it's placed here now, at this point, when we make y the subject by taking e of both sides, so it becomes e to the power of ln y and e to the power of 8x plus c, it becomes y equals e to the power of 8x plus c. Notice how now we have the constant here. This can be expressed as, I'm taking extra steps, times e to the power of c. Notice how because of index laws we would add these two. Now e to the power of some constant is still just a constant. So we can express this as e to the power of 8x plus a, which we can express as a e to the power of 8x. So this is a preferred way of showing expressions that have e, the exponential functions, which if we didn't place it at this point, we would have gotten y equals e to the power of 8x. Okay, and then we could have just expressed it as e to the power of 8x plus c. Now, these are both technically correct. this will just be the equivalent value of whatever this might be. They won't be the same, but they will be the equivalent value giving the same function, but it is preferred that we state our exponential functions in terms of this. Okay, so that's our second example. Now let's pause and give this a go yourself if you haven't yet tried, because now let's answer it here. Now, when looking at this, it seems rather difficult to understand because it's using f of x notation. But if I were to write it like this for you, do you notice how now dy on dx is f of x, and f of x squared is y squared? Perhaps when it's written like this, it's a lot easier to work with. Okay, so let's actually do exactly that. I'm going to multiply both sides by dx. And at the same time, I'm going to divide by y squared. Now this is a little trickier to work with, but if we write it like this, now it's a lot easier to integrate. Integrating both sides, we get 5x, and on the left hand side, increase the power by 1, divide by the new power, which I'll write as just this. So this will give us negative 1 on y equals 5x. Cross multiplying, I'll get negative 1 on 5x equals y. But now take a look at how we might write this. We got 1 on. We could have placed plus c here, or if it were at this point, if we place plus c here, and now if we multiply by y, let me just do this one step at a time, and then dividing by 5x plus c, we could have gotten y is equal to negative 1 on 5x plus c. So notice how where it's placed can really change what it looks like. They are both still technically correct. However, it will just be the case that these values of c, they will not be the same, but they will be equivalent. Okay, but now take a look. The reason why I've shown you this is if we were now to try and use our initial values, f of 0 is equal to 1/5. Take a look at what would happen if we were to try and place it here. So substituting 0 for this, we get negative 1 on 0, 1/5 plus c. This is actually undefined. We cannot get an answer for this one. So this is actually impossible to solve. However, when placed in this one, we get 1/5 is equal to negative 1 on 0 plus c. We get negative 1 on c. And solving for c, we get c is equal to negative 5. So notice how even though we find equivalent values for c, or the constant, depending on where it's placed, some are more correct in that we can solve, well, in this example, we can solve for c given the initial conditions. So the solution, the proper solution to this differential equation is going to be y is equal to 1 on 5x minus 5. Sorry, it should be a negative here. So that is our solution. Okay, so I hope that gave you an insight into solving differential equations where the derivative contains the function itself. So I hope to see you in the next video, and best of luck.